In this web lecture, we're going to wrap up the topic of population genetics by examining the last couple of Hardy-Weinberg conditions that we've not yet looked at. So we've looked at genetic drift and natural selection, the first two on the list. We've talked in class about mutation and how mutation combines with selection and genetic drift to produce changes in allele frequencies. And in this web lecture, we're going to look at both non-random mating and migration. So let's start out with migration. When we talk about migration in evolutionary biology, we're not talking about birds flying south for the winter and then flying back. We're not talking about herds of wildebeest migrating seasonally. We're talking about the movement of alleles between populations. So we're talking basically about gene flow. So individuals moving from one population to another, bringing their alleles with them. And this is going to cause changes in allele frequencies in both of the populations that are affected by this migration. So the simplest way to start to think about migration is by using what we call a one-island model. This is sort of the simplest case of migration. In this model, we have a very small population on an island, so somewhat separated from this large source population on the continent. So we assume that the population on the continent is very, very, very large compared to the population on the island. And as a result of this, there's much more likelihood of individuals moving in this direction from the continent to the island, just because there are a lot more individuals here, and a relatively small probability of individuals moving from the island to the continent. And to the extent that they do move from the island to the continent, the small number of individuals that are going to be coming over is going to have a very, very small effect on this very large continent population in terms of changing its allele frequencies. But the individuals that move from the continent to the island can have a relatively large effect on the allele frequencies in the island population because it's so small. So the migrants are going to make up a greater proportion of the total island population than the migrants from the island to the continent will make of the continent population. So we can say that migration is effectively one way from the continent to the island. Any counter migration from the island to the continent is going to have a negligible effect. And so the question we want to ask is, can migration from the continent to the island take the island population out of Hardy-Weinberg equilibrium? So to illustrate that it can, we're going to take a rather extreme case of this one island model, and we're going to assume that if we look over here, we've got an island population that is initially, this is the beginning of this turn of the generation. So we've got a population of gametes in the island population, and the only allele present in the population is allele A1. So this population is fixed for the A1 allele. Let's say these gametes come together to produce 800 zygotes. So all of these 800 zygotes are A1A1 homozygote. So our genotype frequencies in this population are 1 for A1A1, 0 heterozygotes, 0 A2 homozygotes. And these zygotes all grow up to become juvenile mice in this case. And so still in the juveniles, we've got genotype frequencies of 1, so all 800 are A1A1, and no representatives of heterozygotes or A2A2 homozygotes. So now let's imagine a migration event, and the mainland population, the continent population, is composed entirely of A2A2 homozygotes. So the mainland population is fixed for the A2 allele. So let's say that these 200 individuals move from the mainland to the island. So now we've got a population size of 1,000, 800 of which are A1A1 homozygotes, and 200 of which are A2A2 homozygotes. So now what do we have in terms of genotype frequencies? We've got 0.8 A1A1, 0.2 A2A2, and 0 frequency of heterozygotes. We've got allele frequencies of 0.8 and 0.2. So our predicted genotype frequencies, if this population were in Hardy-Weinberg equilibrium, would be 0.8 squared, which is 0.64 for A1A1, 2pq, so 2 times 0.8 times 0.2 is 0.32 for heterozygotes, and then 0.2 squared, or 0.04 A2A2 homozygotes. So clearly, the actual observed genotype frequencies after this migration event cannot be predicted by the allele frequencies. Not only that, we've got a change in allele frequencies from one generation to the next as we turn around this cycle. And so clearly, this migration event by itself took this population out of Hardy-Weinberg equilibrium and changed the allele frequencies from one generation to the next. So migration is a force that can actually change allele frequencies. This is an extreme case, but in less extreme cases, it will still change the allele frequencies, just not as dramatically. And so if this migration was a one-time only event, a ship happens to carry 200 mice over to the island and there's no regular migration back and forth, Hardy-Weinberg equilibrium would be restored in that population after one generation of random mating. All the alleles will get reshuffled randomly, and this population will be back in Hardy-Weinberg equilibrium with these new A2 alleles, complete with all of the heterozygotes you would expect under Hardy-Weinberg equilibrium. But let's think about what happens if this migration continues at a given rate. The allele frequencies are going to eventually reach some kind of equilibrium frequency, and we can actually predict mathematically what that equilibrium frequency is going to be. So let's see what will happen to allele frequencies over time with steady recurrent migration, generation after generation. First, let's consider the frequency of one allele, A1, that's present in both the island and the continent populations. Let's call P sub I, that's the frequency of A1 in the island population before migration in any given generation. P sub C is the frequency of A1 on the continent, in the continent population. And let's say that every generation, a number of individuals moves from the continent to the island and makes up a proportion M of the island population. So this migration rate can change generation to generation, but in any given generation, the proportion, the fraction of the individuals on the island that are migrants from the continent is M. So the next generation on the island will be made up partially of offspring of parents that were already there, and that proportion will be 1 minus M, right? Every individual is either an individual that was already there on the island, or it's going to be a migrant from the continent. And the frequency of the A1 allele among those would be P sub I. And it'll be made up partially of the offspring of migrants. And the proportion of those, as we said before, is M. And the allele frequency of the A1 allele in those individuals is P sub C. So if we want to know the allele frequency in that next generation, that comes from the combination of the migrants and the island residents, we're going to call that variable P sub I prime. So that's the next generation after the migration. It'll be a weighted average of those two allele frequencies. P sub I prime is going to be equal to this proportion of the population that was already there, 1 minus M, times the allele frequency on the island prior to the migration, plus the proportion of the population that are migrants times the allele frequency of the migrants, which is equal to the allele frequency of the continent population. So if we want to know the change in allele frequency of the A1 allele, it's simply this whole term here for the allele frequency in the next generation on the island, so that is represented here, minus the original allele frequency on the island. That's the change in the allele frequency from one generation to the next. So we can simplify this term by factoring out M, the proportion that are migrants, and what we get simplifying that is M times the allele frequency of A1 on the continent minus the original allele frequency of A1 on the island. So if we want to know what this equilibrium point is, what is going to be the final allele frequency, that's going to happen when this is no longer changing, right? When there's no longer a change in allele frequency from one generation to the next. And so in other words, when delta P sub I is 0. So allele frequencies don't change if delta P equals 0 for the island. So what that would mean is that this term here, M times P sub C minus P sub I, is equal to 0. So when is that going to happen? That will happen when either migration stops, so that would mean that M is equal to 0, or if the allele frequencies are equal on the island and on the continent. So this difference, PC minus PI, is equal to 0. If one of those things is true, or both of them, then the allele frequencies are no longer going to change from generation to generation, and that will be the equilibrium allele frequencies in the population. And so this will depend on the relative migration rates between the two populations. So if we go back to this one island model, what we see is the effect of migration tends to be to homogenize allele frequencies between the populations. Remember, this change in allele frequencies is going to stop when both of these two populations have the same allele frequencies. In this one island model, the allele frequencies are going to reach equilibrium when the island allele frequencies equal the allele frequencies on the continent. Why? Because we said that in this model, migration is effectively one way, from the continent to the island. So there's going to be a large migration in this direction, almost no migration in this direction. Whatever migration happens is going to have a negligible effect on these allele frequencies. This migration is going to have a relatively large effect on the allele frequencies in the island because of the small population size. Allele frequencies on the island will stop changing when they have reached the exact same allele frequencies that you find on the continent. Now, in situations when migration is two-way, it's going to be affected both by the relative population sizes and by the rates of migration to and from both of these populations. So it'll be a balance between the two. With equal population sizes and equal migration rates in both directions, you're going to get equilibrium allele frequencies that are exactly in between the two allele frequencies in the two populations. So again, the overall effect of migration is going to be to create equal allele frequencies in both of those two populations. So if we think about the diversity component of this, what does this do to genetic variability? We said that the only way to create new variability is mutation, but we said at the population level, migration can increase genetic diversity, and we saw this quite clearly in the example we did in class with the collared lizards. We saw it in the example with the American bison, that we were able to create more genetic diversity by creating migration or gene flow between these separated subpopulations. But what we also find is that migration can be a means of maintaining a stable level of genetic variation. And so I've added here to the end of this list not only mutation selection balance, but also migration selection balance. And so what this means is if you've got two populations with different kinds of selection happening, let's say that an allele is being selected against in one population, but you have constant migration from another population where that allele or that trait or whatever it is not being selected against, then you're going to maintain that phenotype, that other allele in the population in spite of the fact that it's being selected against, because you've got this gene flow coming from another population that maintains that allele in the population. And we'll see an example of this in class.